All right, thanks everybody for joining. Today we're very happy to have Siem and Koopman from the VU University in Amsterdam, and the discussant will be Creal from Notre Dame. And Simeon's going to talk about Extremum Monte Carlo filters. And you have 1 hour, Simeon, when the floor is yours.
Great, thank you very much, Geert. Many thanks for the invitation to present in this very impressive series of virtual time series seminars. So I thought it was a great initiative, and I'm now very happy to be a part of it. This is a paper that I'm going to present. Is joint work with Francisco Blasquez and Karim Moussa. And Karim is our PhD student, and he's going to defend his thesis, I think, 2 weeks after Easter. So that will be basically in 2 weeks' time at the VU. And well, we're all looking forward to that. And one of the sort of the key papers that came out of his PhD research that is this topic of Extremum Monte Carlo filters, and some future work. I will discuss that at the end of the presentation. So well, let's go. My presentation is built up that in the first sort of set of slides, it will be more like introducing the issue of filtering in state-space models. So I give a little bit of an overview for those who are not so familiar with the literature, and then I move on to the sort of the new bits that we are proposing in this paper. So there's a bit of like my own sort of reflections on the filtering of non-Gaussian and nonlinear state-space models, and then I move on to the topic of Extremum Monte Carlo filters. Well, I already told Geert I'm happy to take questions during the presentation, so you can stop me, or at least Geert can stop me whenever he likes. Well, everything was working on the testing. Yes, still working. So this is the content filtering, introducing nonlinear non-Gaussian models and filtering, then move on to Monte Carlo filters, and then some applications. So the topic of filtering, well, when we consider this sort of Gaussian local level model, a model that we often use as a vehicle to explain the intricacies of state-space modeling and Kalman filtering, is that we start with this very stylized model of the local level model, in which YT is the observed or measurements. So these are the observations, these are the actual time series of interest that you like to model. And then in this particular model, we have a time varying mean or a level that is time varying xt. And we have an epsilon, the usual noise that is not explained by the trend or by the level. And the superscript y just emphasizes that is corresponding to the y, and the other epsilon is epsilon x, and that is corresponding to the random walk. And the random walk is a model for xt, the actual time varying level. So it's basically just a mean plus noise model, but the mean is time varying according to a random walk. The initialization is typically diffuse, but I sort of avoid that discussion for today. So I'm just saying that we have some particular mean and then variance upon which we start off the filtering for x. So the initialization for x1 is just assuming that it is coming from, in this case, a Gaussian distribution with a fixed mean and a fixed variance. And you can treat these coefficients for the moment as sort of unknowns that we can estimate by maximum likelihood. But again, that is only just to avoid the discussion of diffuse filtering. So that is the notation. Xt is then the states, yt are the measurements, the observations, and the two epsilons are the noise terms in the observation and state equation. And then we collect typically all the unknown coefficients in a parameter vector. I call it here theta. And as you can see, the mu and the sigma 1, the initial conditions, and the two variances are treated as unknowns. And we just compute them, or for the moment we just assume that they are given. So this talk is not really about how to estimate theta. It is much more to how to compute that conditional expectation there in the display of the equation. So the whole focus of this presentation is about this animal, about this entity, the conditional expectation of the level xt given the past and possibly also the present data points. Yeah, so that is what we might refer to as the filtering problem. Well, it is sort of a very practical type of problem filtering. It comes back in all kinds of applications, both in economics, in engineering, in computer science. So in all kinds of different fields, people are sort of interested in the filtering problem. What is the signal and what is the noise, and how to separate the two using a statistical dynamic model. Well, that sort of problems, they come in all kinds of different shapes and forms. So it is a generic problem that we are tackling here. And then I should also say that in a Gaussian context, because the model as I presented it to you is linear. So we have that the level is a linear in the observations. We only add some noise, and the updating equation is also basically just linear. It is a random walk process. And all the noise terms are coming from a Gaussian distribution. So the model that I just presented to you is a linear Gaussian model, and we basically can say it is a specific example of a linear Gaussian state space model. And for that kind of family of models, the filtering problem is, of course, already solved many years ago by Koopman, and that has sort of been resulted in what we now know as the Koopman filter. And here I present to you the Koopman filter for this particular local level model. But the entities that are given are sort of generic. We have always a Koopman filter with sort of starting with a prediction error. So that is the VT here, the prediction error. This is the predictive estimate, the conditional xt given the past data. So we can assume that we can define the VT as the prediction error, and FT is then the variance of the prediction error. And that is a function of PT, where PT is the conditional variance. So if this is a conditional mean of the state, then PT is the conditional variance of the state. Well, the filtering itself, so this is the prediction one. If you then want to get the filtering one, this one is then basically the predicted one plus something like that we learn from the prediction error. And so we are weighting the prediction error here by PT over FT. And very often we just call that the Koopman gain. So we give it a certain weight. And then we get the filtered estimate. And we also get the filtered variance, so as a function of PT and the variances of the model. And we can then, once we have the filtered estimate, we can also make a prediction of the level tomorrow based on the data of today. So we get a new prediction for tomorrow. And that is basically then the same as the filtered estimate for this model. And we also have a predicted variance, which is the same as the filtered one, plus the uncertainty due that we are going to the next period for the level. Yeah, so this is sort of like, if you know Koopman filtering, this is of course all very standard, but yeah, here we go. Here I do initialize with sort of a diffuse thing. So here implicitly I do not estimate the mu and the sigma one, but yeah, this I think it's so standard in my mind to use to initialize the Koopman filter by a diffuse prior. So I just copy pasted that here. Yeah, so this is the Koopman filter for a standard linear Gaussian local level model. And then in the book we are using chapter 2 the null data, and that is sort of like a nice illustration of how the filtering goes for specific choices of the two variances. And this is sort of the typical picture that you get. The blue line are the observations, the volume of the Nile, the average volume of the Nile over the years of 1870 up to 1970, so 100 observations, and then we plot the filtered estimate of the underlying level. Well, sometimes we refer to this as signal extraction, and that is typically what the Kalman filter does in sort of like the filtering sense, prediction and filtering. And from that, we can get prediction residuals. And if we believe in the formulation of the model as being a statistical model, as a good reflection of how the data has been generated, then we can also attach statistical properties to these prediction residuals. And for example, assume that they should be white noise if the model is well specified. So we can test for whether the prediction residuals have no zero correlation, whether they behave as coming from a Gaussian distribution, whether they are homoscedastic. So you have all kinds of diagnostics to check whether the prediction residuals behave in a way that is according to the model that we have used for the particular time series. And once we are sort of satisfied with that part, then we can think about practical things like detrending the data, take out the filtered estimate or the smooth estimate, and then use the detrended data if we are wanted to focus on other things than the trend. Or we can do something like forecasting. We can look ahead, so extrapolate the dynamics into the future. And all these sort of like applications, also log likelihood evaluation, can all be done by the Kalman filter and what I call related methods, but I basically mean smoothing algorithms to, for example, do the detrending or do the deseasonalization. If the data is subject to seasonality, we also account for seasonality in the model, and then you can use the Kalman filter to extract the seasonal component. And we typically do that via smoothing and then sort of use seasonally adjusted data. So all these sort of practical things that you want to do with time series analysis are very much all handled by the filtering, by the Kalman filtering. And therefore the filtering sort of takes a central role in state-space analysis. Well, one of the features that I always like to highlight is that you can deal with missing values in Kalman filtering, and basically give you all these illustrations and sort of the things that you can do with the filtering, because also for the Extremum Monte Carlo filter that I'm going to discuss later, we'll all be able to do this. We'll all be able to replicate all these nice features of the Kalman filter, but then in a more general setting. So that's why I go through all these sort of like standard applications of Kalman filtering, just to remind ourselves of the powerful, technical tools that it provides, and we like to preserve that also for models that are non-linear or non-Gaussian. Okay, so that's what we are now entering, the challenge of non-linear and non-Gaussian filtering. And I'm fully aware that there are already many different types of solutions, solutions that are sort of coming from 30, 40 years ago, but also like solutions of last year or the year before. It is still a very active research area. So I will just give you a quick overview of the types of solutions that are put forward in the past before I continue with the Extremum Monte Carlo filter. So here I present to you the nonlinear non-Gaussian model, the most general model that you can think of, basically, because we have for yt a nonlinear function mt, mt standing for measurement, so the measurement equation. And the measurement equation is basically a function that has as inputs the state, the xt. And here the xt is really like a state vector, so not necessarily a random walk level, but it can also be any sort of dynamics can xt contain, and it can contain multiple dynamics, so xt can be a vector. So it is really like a state vector. And the same here for the epsilon. If you have multiple y's, then typically also have multiple epsilons needed to take care of all the stochastics in the data. So this can also be a vector. So everything that you now see basically on the screen, all these different entities are basically vectors. Generally, they can be vectors. And I'm going to illustrate the methodology later also where we have like a long vector of time series here in YT. And of course, if this is a vector, then this is a vector function. So empty can be a vector function, and inside of the vector function, there is also a vector xt, the state vector as input, and a disturbance vector as input as well for the measurement noise. Well, the xt is following some dynamic process, and the dynamic process can also be anything. So it is not necessarily a Gaussian linear process that we often sort of assume for the state, but in this sort of context of well, let's say particle filtering, nonlinear filtering, we also allow the dynamics to be anything that you like, so to say. So there can be some kind of a nonlinear mapping. Typically, it will be a vector function, and st will be a vector function, and again then an input of a vector, and epsilon tx, the noise term for the axis, is then also a vector. Well, this model has also been studied in this type of generality by many authors in the past. So there are many papers that deal with this kind of generality in the filtering literature. And here's one example, but I will give later on some more examples of that. Well, some motivation, at least that came into my mind, are these time series. Well, maybe not so much the null data, although there are also some, if you look at longer time series of volumes, also some non-linearities that can be sort of part of the data. But for non-Gaussian data, I can think of ones and zeros, a binary time series. Here I have the time series of the boat race. Probably that Geert also knows that very well, the boat race data. The ones and zeros, which is a highly non-Gaussian time series, but clearly also some dynamics. You can see the patches of ones and zeros all over the place. So there's some predictability in this time series. Of course, the most obvious example is the volatility time series, where we're basically not modeling the mean, but the variance. And that is also typically either a nonlinear problem or a non-Gaussian problem. And so that is what we are illustrating here. The lapwing data that has also some sort of boundaries that you cannot, this is basically a date. So this is sort of a funny time series where you look at when people found the first egg of the season for the lapwing, the bird lapwing. They produce these eggs, and then you can record when the first egg was found, and then you sort of get a time series. But there's sort of time limitation, so it has not sort of a big variety of movements. So you should also address that type of variation. So this is the month, this is the day in March, the 30th or the 10th in March. There is a zero observation. It was basically the last day in February, but all the other days are in March. And you can sort of see the influence of climate change, that the lapwing is producing the eggs earlier and earlier throughout the last 20, 30, 40 years. And that is just because of the climate change issues. So this is another illustration of what the effect is of climate change on birds. So these are all sort of interesting time series on their own, in their own merit, but at least it is a motivation for us, I think, to look at nonlinear, non-Gaussian models and do the filtering. Oh yeah, and well, also this, what I call bread and butter economics data, the US inflation, of course, the most important economic time series or economic financial time series that we probably want to analyze. And also in this time series, there are many features, both in the mean and in the variance, that can be either treated or need to be treated as something nonlinear or non-Gaussian. So I think there's enough motivation, even only in the US inflation data or in any inflation time series. But so yeah, I think that sort of provides sufficient motivation to do the challenging thing of filtering in a nonlinear, non-Gaussian context. And again, the filtering problem can be simply formulated as being just focusing on this conditional expectation. And of course, the whole whole density, basically, I should take. But well, in the end, we are typically always interested in the conditional mean. But what I imply by this is also the whole density, so also the variance and the other higher moments or the quantiles of the conditional density. So that is all also included in the whole methodology as such. But anyways, the filtering, as we know, sort of know, it is always focusing on this conditional expectation. And then not applying to the sort of linear Gaussian local level model, but now applying to this general state space model that I just have been introducing to you. And then the sort of the techniques that you typically comes in mind when you look at this problem and you do some literature search, you come up with solutions like the extended Kalman filter, Monte Carlo techniques, such as importance sampling, but also Monte Carlo techniques. And I think nowadays this is sort of the main default, the main method of tackling this problem of filtering in a non-Gaussian nonlinear setting, the particle filter. And that is sort of, I think, but as I said, there's also some more recent sort of techniques that come available. People nowadays also treat it using machine learning methods. So there are all kinds of different techniques around these days that tackle this problem. So this is definitely not a resolved issue as such. So I think there's still many challenging problems for doing nonlinear non-Gaussian filtering, and one of them is that when the state space model has limited tractability, and so for example in the particle filter you need to simulate from conditional densities, and sometimes you have models where conditional densities don't exist because they only have a first moment. So that sort of issues that can make current methods somewhat challenging. When the state vector is high dimensional, so if you are typically treating seasonality in univariate time series models or high dimensional problems in multivariate problems, then particle filtering tend to be always working somewhat challenging. It's somewhat challenging then to implement the particle filter and to make it work in the way it needs to work. So that is, I think, still an issue if we have large state vectors, then how to resolve the nonlinear non-Gaussianity. And of course, the real-time constraints, the computer time, how much time there is available to do all this type of work. Yeah, so there are still some challenges to resolve. That is what I think I want to say in this slide. Well, the extended Kalman filter is sort of like the most classical solution for at least nonlinear state space models. So maybe we can still assume that the errors are Gaussian, but then we may have some nonlinearities in the measurement equation or in the state equation. And then if we want to tackle that, well, we then basically can do a Taylor expansion on both of these functions up to the first order, and then use the mean to concentrate around that first order Taylor expansion. And then basically, if you apply that to the Kalman filter, you get what we call the extended Kalman filter. And well, I think where it comes from, the extended Kalman filter is very much like something that is obvious once you think about the Taylor expansion and you just do the analytics. But in the book of Anderson and Moore, it is explicitly mentioned and all the details are provided there. So I think basically already in the earlier work of Kalman, it was already mentioned that you can also approximate this sort of updating using Taylor approximations. So that is what we then call the extended Kalman filter. And then apart from the Taylor order expansions for the mean and state equations, the variances, the updating of the variances, that is still the same as for the Kalman filter. So that is sort of the detail without really giving you all the details, but that is just what the extended Kalman filter does. Then with the advent of Monte Carlo methods, we started to use these Monte Carlo methods basically to directly evaluate this expectation. Can you just give me one moment, just a pause of 10 seconds. Sorry, this was the 10 seconds that, for the break that I needed. So yeah, so doing a straightforward Monte Carlo method that is sort of with the advent of computer power becoming sort of a feasible thing. And I think that the sort of the box standard way of doing Monte Carlo is just evaluating basically just using the definition of expectations, and then actually doing it by randomly choosing x's. And well, the x's can be just taken here from the actual density, the filter density that you're interested in. And you just simulate many of these, and then you take the average, and then you sort of have an estimate, a Monte Carlo estimate of that filtered entity that you're interested in. And well, the more M you take, the more precise it gets. And the nice thing of straightforward Monte Carlo estimation is that it leads to a consistent estimator, as you can see here at the bottom of the screen. The only thing, of course, in the analysis, as soon as you start thinking about nonlinear non-Gaussian models, we don't really have an analytical form for this conditional density. That is, of course, the whole filtering problem. So this is fine if you have a linear Gaussian model, because then you know that the conditional densities remain Gaussian, and then you can do this Monte Carlo, although you really don't need to do it because you have already the Kalman filter. But that is, of course, the issue, that you cannot really take these draws. Dus that is a bit like an issue for doing straightforward Monte Carlo estimation. But then what people have done, if you don't have this closed form expression for Monte Carlo estimation, you can take this importance sampling method, and that is, of course, what I have discussed over the years, and has also come basically as has been all put in part 2 of the Koopman book, where we basically discuss this technique of importance sampling, where you basically take an approximate of the filter density or the smooth density as we used it. We take an approximate of this density, which we call then the importance density, and then simulate from that. And if you have that in an analytical form, you can just choose x's randomly from that density, and then account for that approximation by weighting the actual simulated values. So this is a nice technique in the sense that you still have the consistency of the estimator, but of course it relies very much on the approximation of the importance density. So how accurate is this approximation to the true density that you're interested in? So that is sort of the idea of importance sampling. You can do that for every t, so to say. So you can do it for a filtering sense, but of course then you need to do sort of the Monte Carlo approximation for every t, and that can be somewhat time consuming. And therefore I think I would dismiss this method for filtering. For one-off smoothing, it can be used, and that's also how we use it. And for likelihood evaluation, you can use these type of methods. But for really actually online or real-time filtering, that is basically just asking a bit too much, and it's sort of less elegant to use it in a filtering sense. Yeah, so that is sort of the technique of importance sampling. As I said, there's some old literature on these methods, and also the associated technique of how to get these samples from approximate Gaussian densities are evolved over time and presented and used in practice. The particle filter is basically sort of like an online sequential way of doing importance sampling. So therefore, I think it's always good to first give the idea of importance sampling and then sort of switch to the particle filtering, because that is an online sort of version of the ad hoc importance sampling technique, because there you build up the importance density sequentially. So you basically throughout the time you create approximations that are as close as possible to the true density that you're interested in. So here I give the what we call the most basic example of particle filtering or sequential importance sampling, as it's also known in the engineering literature, or even known as the bootstrap filter, because it's the most simplified version of the particle filter. And that is well, really so easy that you can code this in a few lines in Python. And so it is a very accessible way of solving a very intricate problem for non-linear, non-Gaussian state-space models. So that, as you can see, it is again an important sampling weights that you need to create from the measurement equations, basically to see how well the particles fit to the data at time t. We did it for a sequence of m particles, or for a whole array of particles, and then all these weights basically give some indication of the importance of the y's, well, the importance of these xc to the yt. And then you compute, you weight all these particles using these weights determined from the density, and then you get an estimate for xt hat, and that is basically the filtered estimate for the state vector. And just to make sure that you're are not sort of going well, converging to only a few particles. You need to keep the particles alive, and then you can do some redrawing, some resampling, and that's basically redrawing the particles with replacement, so you can get many copies of the same axis, but you sort of get them where the most weight is. So that is a good way of keeping the particle filtering sort of providing enough support to the whole density. Yeah, so that is the well-known technique, what is known as the particle filter. Well, here I give this example for the null data, but I'm sure that you have, many of you have already implemented it for much more challenging problems than for the null data. So the nice thing of the particle filtering is that it provides a very general and highly effective real-time methodology. It does Bayesian inference. It can be incorporated into Bayesian inference quite easily and also naturally, I would say, because it is all based on simulations. And Bayesian inference, the most practical Bayesian inference, is also based on simulation, micro-chain Monte Carlos. So if you put the two together for dynamic filtering problems, then a paper about now more than well, about 14 years ago is presented and known as the particle Markov-chain Monte Carlo method, and that basically gives you a full solution to doing Bayesian inference on a nonlinear non-Gaussian state space model. A big impact has it on it because it really opens the way to do in a relatively simple way of getting an inference for a highly non-linear non-Gaussian model. So I provide some references to this literature and also some excellent reviews on this literature. So for those who are not interested, there is a lot of literature. Well, now adding to this sort of like old literature, although I'm also fully aware that there are also other developments in tackling the problem of nonlinear, non-Gaussian filtering. But what we are proposing here is basically another Monte Carlo method, and you can basically also call it a crude way of doing Monte Carlos. Is basically just simulating a lot of data from the model and then selecting all this simulated data from the model by using a regression and then determining which paths are appropriate to use. So that is what we call Extremum Monte Carlo. And it basically combines unconditional simulation with regression techniques. So for this way of filtering, we can sort of try to claim that it is generally and conceptually very straightforward again, because it is basically only simulation and regression. And I think we're all familiar with these two concepts. It circumvents the tractability requirements for many of the simulation techniques that I have been discussing so far, that we basically both the importance sampling and the particle filtering, they are based on having the existence of a conditional density. So we need to have a conditional density, a filter density from which we can simulate numbers. And that requirement, if you only need to sort of simulate from an unconditional model, from an unconditional density or distribution, then you basically can just simulate straight from the model. So you don't need to really have that requirement. Well, we can use the latest versions of machine learning, because regression, nonlinear regression, because that's what we need, is rapidly developing in the machine learning world. So we can basically use all these techniques from there to do the actual regression after the simulations. And that basically both means that we can use regression techniques that can address high nonlinear entities, but also the computational speed can be increased a lot by using all these latest developments. It is fast in real time, the technique, because most of the computations can be just done offline. We can just night and day, we can simulate data from the model and do the regressions. That is only artificial data. And as soon as the real data comes in, then the computations are very, very small and minor. And so we can do quick online filtering. So we basically make a separation between sort of offline calculations and online calculations. And the offline calculations, of course, are a bit heavy because you need to draw all these numbers and do all the regressions. But as soon as you're online, you can just do the calculations very quickly. And the offline computations that are needed can all be done in parallel. So then we can use all the parallel power of computers nowadays. Well, XMC, what I'm going to discuss today is just the filtering only. So we're only discussing the filtering, but forecasting, smoothing, and treating missings, that can all be done within this new framework. So what is the idea? Well, the idea is not really new. It is coming from Longstaff and Schwartz in a finance paper, Journal of Finance. And basically what they did for option pricing, because in option pricing you also have these sort of nonlinear mappings between the price and the options. And they wanted to have sort of like let me call it a sort of a non-parametric way of getting that nonlinearity out. They basically simulated many random variables, just as I display it on this slide here. They simulate many data points from the joint density, X and Y, so X and Y being two variables. And we know how they are related from a sort of model perspective. They are dependent on each other, so we have formulated a joint model for X and Y, and then from that joint model we are simulating like capital N number of draws, a pair, N pair of draws, so to say. And for each of these for all these simulated pairs, then we are going to perform a regression between them, and then we basically get a regression estimate for all the X and Y's. And so we get basically an F hat being here the beta hat, so to say, for a regression model, and for a linear regression model. And well, if you take the loss function as a squared loss function, you basically just get least squares, OLS. But if you, of course, take another loss function, you do another type of another type of estimation, median estimation, mode estimation. That's all. So depending on the loss function, but for the moment we just only consider squared, the squaring as a loss function. So it is just a regression thing. And then once you have the real data, then you can use the real data to use the beta hat that you obtained from the simulations, doing the regression from the simulation. And then you basically predict from Y the X hat or the beta hat that creates the estimate. Yeah, so that is the standard technique that at least in Longstaff and Schwartz paper they pursued, and that is for a static regression, so to say, for two variables. And basically what we do in the paper is just to generalize this to a time series of X and a time series of Y. And then the time series of X being the states, the level that I presented to you earlier, and Y being the data. So in the local level model, Y is X plus epsilon. That is all of the two entities. So we are interested in estimating X using observations Y. So so it's just what I said. The idea is simply to create vectors of X, and I use here the notation to emphasize that it's really a sample of a whole path of variables X and Y, and of course X and Y are from the state space model that I introduced to you earlier. So these X's are drawn from the general nonlinear model and the Y's as well. And we simulate N of these paths, capital N of these paths. Then we regress, and now you have to be careful. The regression is not really over time, but it's really over the index I. So just think and see in imagination all these paths, and then you basically look at the vertical line. So the horizontal line are all the time series that you see, and then we do the regression over each vertical line for each time point t, so to say. And then we use this regression over all the samples over n. So the regressions is going to be over n. So this regression thing is over n. That is the sample size for each t. So that is really non-time series, so to say. So we're not filtering as such. We are just doing the straightforward regressions for each t over these cross sections of Y variables. That is sort of the technique that if you want to generalize the technique of Longstaff and Schwartz in the Journal of Finance paper, that is how that should work out. And then we evaluate all these estimated regression functions at each time point t. Well, as I said, by changing the loss function, you get all type of different estimates depending on what you're interested in of the density. Here, I basically focus all the time on the mean, on the expectation. But if you're interested in quantiles of the filtered densities, or you're interested in the skewness or the kurtosis of the densities, then you can use all kinds of other estimation techniques, quantile estimation, mode estimation. So all kinds of different estimators can be used in this context. And that is, of course, also why the whole library of machine learning techniques come in very handy, because they can tackle all these types of different loss functions over I. Well, then the first thing I always then ask people, if they come to me with these sort of like new great ideas, well, just apply it to the local level model and the null data, and then I'm convinced. And that is just what we do here. So we basically take the null data and the linear Gaussian local level model. And yeah, you basically get here all the simulated values. So these are just some simulated x's. These are the corresponding simulated y. So here n is 3, but for this picture we have n is 10 to the power 4, so 10,000 of these. And then just took all the estimates and plot them, and then the estimates are aligned in this line here. The same line is the Kalman filter. As you can see, the red line is the Kalman filter, and the dotted blue line is the linear XMC, the Extremum Monte Carlo filter estimate. And you see they are really aligned. And maybe you can still see some color differences, but that is because of the dashed line of the blue one. And if you really want to see them numerically, then and you're not satisfied, then you can still raise the power here to get more ends, because these simulations are so cheap from a random walk and an additive error. So you can easily do this multiple times to get it exactly the same. But yeah, for 10,000, it sounds like a big number, and I agree that that's also what we are still struggling with. It's so many numbers, but of course the computations are very fast because it's all unconditional. It's just getting random numbers and then putting the random numbers in place to get them to get the data. And the regressions are very fast. In this case, it's just OLS. So you just do all these OLS for every t, and then you basically get the line over here. So in that sense, it is a straightforward way of doing the implementations. So these are the sort of the properties that we like to highlight in this method, is that they are generally applicable, because here I did it for the linear Gaussian local level model, but the same ideas can be done for any other type of nonlinear model. Just simulate the data, put it in the nonlinear mapping of either the measurement or the state functions. So basically, it only requires the ability to simulate from the state space model. That's all what you need to do. So as long as you can simulate from the state space model unconditionally, then you're basically in business. Well, the regression methods that often work well are gradient boosting, because they a very efficient way of getting your estimates, but also random forest and neural networks have been used in our paper to show the case that it is very flexible. You can basically just choose your own regression technique that you like to apply that to within this method. Well, most computations, as I said, can be performed in advance. It's both the simulation and regression. As you can imagine, you only have to give me the model, and I don't need the data because I simulate all that data. Then I do all the regressions, get my functional estimate. And once I have the functional estimate, then the only thing I need to do is just wait for the data to arrive. And as soon as I have the data to arrive, I put it in the function and to get my estimates for the state. Yeah. So in that sense, it is all straightforward in an online setting. Well, of course, you need to do this sort of for every t, and in the typical example of, for example, in financial econometrics, the capital T can be like 10,000 or so. You can have many a long time series of financial returns in high frequency data. And then it would be nice that you don't have to redo all these nonlinear regressions for every t. And then we have found out that there is something like working and steady state filtering, because basically what happens here is that for the filtering, we not only use, because maybe that I put you on the wrong foot there when I said that you just use only the data, you do the estimation for every t. Well, that is what you do, but you don't only use the data of yt that you have simulated, but also yt-1 can be used that you have simulated, because that is the past data and that is available also in real time. So you can use also yt-1 that you have simulated, yt-2 that you have simulated. So you use sort of a window of data of the past. And you also put it just in your machine learning technique, and then the gradient boosting will find out which ones will have the most are the most powerful in explaining the state that you have simulated from the model. So you basically get these regression functions that also use past data, but of course you repeat it for every t, this thing, so it will become a function. Well, and once you have enough data of the past used for doing these regressions, it's basically just a repetitive exercise that you do. And whether you do that simulation numbers at time t equal to 5, well, maybe 15 or 20, or you do that at time point t is 20, 30 or 40. The only difference is all these different random values. So once you know the regression estimate, and the model has not changed its structure, so it is a time invariant model where the function of S and the function of M, the state function and the measurement function, don't change over time. So the structure of the data locally is the same. Well, then these estimatable functions are also stable. The only reason why they are not stable maybe at the beginning, because you just don't have enough data at the beginning to estimate the full function that you want to use, the full amount of past data that you want to use, or that is selected by the machine learning method. So at some stage, when you're enough sort of into the data, into the time series dimension, then you can at some stage stop with the regression estimation, because you basically have the regression function solved, and the underlying dynamic structure will not change in the future. So you have something that we call then also steady state filtering, because it is exactly what happens in the Kalman filter. Once you have a time invariant filter, the Kalman filter, the gain function will become a constant. If you have enough past data, then the weighting function will stabilize, and then it will just carry on over the time series dimension. And that's what we call a steady state. And that is what we also find here in the XMC filter. And particularly in the XMC filter, it is really worthwhile, because it just takes a lot of computations out, because you don't have to repeat all the regressions over the simulations. Yes, so many computational savings can be made, and they can be substantial if the model is heavy enough. Yeah, so I think I've more or less discussed this slide and this nice feature. This is sort of the way we check whether the steady state is achieved, whether you have sort of enough data points here such that the loss function at different at the time point t is the same as if you would have at the endpoint at the final time series t. So if that loss function doesn't change, not anymore in time, then you basically have a steady state. And the steady state, you try, of course, to find that as early as possible in the sample. And that's so this is something that you do initially in the sample to check whether it does not get bigger anymore. All the way of doing these techniques, I already referred to the machine learning techniques. That is also where we sort of use the technique of validation and testing samples. So for the estimation, we do an estimation sample, and then we have a validation sample for example, to compute the loss functions. So that is also separated out, these two things. And so it is really adopting all the machine learning techniques that can be adopted. Well, here we show the gains that you can get for steady state filtering when we apply it to a fairly complex model, the stable S3 model, or at least non-linear. And you can see that whether we apply the steady state solution or whether we don't apply the steady state solution, you basically get the same thing here. And because, as I said, this model, the dynamics don't change. It is a time invariant model. So you basically get numerically exactly the same techniques. And here already at the time point 21. And so basically means that you only have to do the regressions for this part, and you only have to do the simulation for this part. So here you do simulation and regression. And from here onwards, you only do the simulation and apply the same regression thing that you already have computed earlier. Well, as I said, it can handle missing data fairly easily, because of course, as you can imagine, this is all T by T type of regression estimation. And if there's no data, then it basically just relies on the previous estimate, and it will not change anything. This is of course fairly obvious for a local level model, but it will also remain to have the dynamics of the system in. So if it is a nonlinear dynamic, it will then of course evolve as a nonlinear deterministic system over time in the process. So it can deal also with mission observation. Of course, you need to do some handling in the algorithm, but it can be handled. Well, from the properties of the filtering is concerned, we can show some properties, although it is, of course, a highly numerical technique. So to say something theoretically about the methodology is very much relying on the regression technique that you use. So basically, the properties that the regression technique has can basically be adopted also in this technique, because you basically repeat it only over time. The same technique. So you basically copy paste also the properties of the regression techniques into your filtering. The only thing that we wanted to show here is that the filter, if you repeat it and you use the past data in this thing, that it will lead to a stable filter. Yeah, that is sort of like an important property, that the filter is stable over time, and that is, according to this definition, we can show that it is that the errors from the filtering are bounded for to different degrees of p. So that is also the thing that we wanted to show here. And there's a small appendix that shows this property. And another one that I was very eager to show, that if the state-space model, the general state-space model, is linear Gaussian, that the XMC will converge to the Kalman filter in a relatively fast way, to the basic standard rate of square root capital N, so the number of simulations. So that basically means that the number of simulations are relatively limited, so you don't really need to have an extensive, the large capital N. But again, these are sort of like two properties that I think are useful and are comfortable to have, but are not sort of vital to the algorithm. Well, just in the last 2 minutes that I think I have, or 3 or 4 minutes, let me just go quickly to the applications that we have considered. One is the stochastic volatility model. Well, you might say, well, that is handled by so many different techniques, so it should work. But the only sort of exception is the stable distribution there. So if you take a stable distribution, like an extremely heavy-tailed distribution is the stable distribution with these two coefficients that we have in there, so tail coefficients and the asymmetry. Typically, the stable distribution is only considered for the tail, but here we also use the asymmetry of the distribution, so we also estimate the beta in this way. And the idea of, or the challenge of the stable is that conditional densities don't exist, because it doesn't have moments, so we cannot really do very much with this stable distributions as soon as you start conditioning on data. And therefore, you can only rely on it as an unconditional density, and that's basically what we only require for the technique here. I know that if you're very much in particle filtering, you can still deal with this model by using some approximations. You can basically take a very heavy-tailed other distributions from which you start running the particle filtering, and then still apply it to the stable distribution. So I fully understand that there are sort of other ways of solving it, but at least for the conditions that we need for the XMC filter, this is at least a case that it is very natural to take, because we don't need to we don't need to we need to do simulation, but not from a conditional simulation. And so okie dokie. So once we do that, then we basically, because we have not really discussed the estimation, so we just took the coefficient from the Venkov paper that also has dealt with the stable SV model, and also has a methodology to estimate them. So the static parameters are basically taken from the Venkov paper. And then we basically did a technique and compared it with the QML filter of Harvey et al. The QML filter can be used here because it doesn't take any assumptions about the distributions of the errors, so we can basically compare it. And then we looked at the root mean square error of the state, of the conditional state thing. And you can see that our estimate, if you consider the stable thing, really leads to a much more precise estimate. So that is an illustration of it. And as promised, and this is the last illustration for the last minute, is the high dimensional filtering case, where we look at a high dimensional vector YT and then similarly high dimensional vector XT. And we basically just taken a very simple VAR model for the state, for the multivariate state. I just want to filter the X's out of this VAR plus noise model, and the noise is coming from a Gaussian. So it will sort of like artificially make it a bit difficult, and then just doing the filtering with the XMC and with the particle filtering, or the bootstrap filter in the multivariate sense. And then if we take the dimension, the D equal to 25, and we take 10 to the power 4 draws for our XMC filter using the general boosting, gradient boosting algorithm, then you can see that we gain a little bit in sort of precision of the estimates of the XT for the filter, but not very much for the compared to the bootstrap filter that we have implemented. But if you make the dimensions somewhat higher, you can see that the differences become larger, and therefore the nice thing here to see is that basically the root mean square error for the XMC filter remains stable for different dimensions of D, and that is sort of the message that we wanted to bring home in this filtering paper. Oh, even 200, as you can see where the particle filter diverges. And so this is the conclusion, basically introducing this new technique of doing filtering for nonlinear, non-Gaussian models. And the forthcoming work is, of course, the extension of smoothing and looking at simulation smoothing, also that we are able to simulate draws from a more complicated model. So all these techniques can be also applied to this more general setting. But this completes my presentation here.
Thank you so much, Simeon. That was wonderful. Yes. So let me first give the floor to Drew to share his comments, and then afterwards we'll open the floor for some general questions, discussion, whatever people have. Drew, go ahead.
Okay, so this is a really nice paper, at least the version of the paper that I have. I've read it a few times, which gives me some questions and things maybe I don't understand. First is like